Good afternoon, everyone. I'm Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar series. This is part of a new graduate series we are running in partnership with the Association of Canadian Ergonomists, or ACE, as they are more commonly known. We are grateful to the Ministry of Labour, Training for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. We are using a new webinar presentation format, and therefore we ask that you keep yourself muted for the duration of the webinar. Use the microphone icon in the control panel that appears near the bottom of your screen to mute yourselves. During the question and answer period, we ask that you type your questions into the chat box, ensuring that it is highlighted to everyone. The chat box can be pulled up on your screen by selecting the chat icon in the control panel that appears near the bottom of the screen. The questions will be relayed to the presenter or a similar question should there be duplication in themes. Should you have a pressing question or issue such as a technology glitch that cannot wait until the end of the presentation, please type this into the chat box and we will do our best to address it right away. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a question and answer period. This webinar will be recorded, with the recording being made available to you on our website along with the presenter slides shortly after today's webinar. You will be sent a link to an evaluation after the webinar, and we ask that you fill this out as it will assist us in the future delivery of our webinars. Now it is my pleasure to introduce to you our presenter today and then hand it over to her. I'm pleased to welcome Chelsea DeGuzman, who is a third-year PhD student in the Human Factors and Applied Statistics Lab at the University of Toronto, and she is also co-president of the Human Factors Interest Group. Her PhD research focuses on drivers' understanding and the use of automated driving technology. Chelsea is particularly interested in how to improve drivers' understanding of driving automation to reduce over-reliance on these systems. Chelsea received her BA from Western University, specializing in developmental cognitive neuroscience, and then completed her Master's of Science at the University of Toronto in Human Factors. Thank you so much, Chelsea, for joining us today, and we look forward to your presentation. Over to you.
Thanks, Catherine, and thank you everyone for attending. So Chelsea, I'm a PhD student, and I am supervised by Professor Birsen Donmez at the Human Factors and Applied Statistics Laboratory at U of T. And today I'm going to talk about my research on automated vehicles, specifically how drivers respond to different failures and what they know about the technology. Start with a little bit of an introduction, a little bit of background on me, although that was covered a little bit, and a background on the lab. And then an overview of advanced driver assistance systems. So these are systems that can control steering, acceleration, and braking for you. And then we'll get to the two studies I'll be talking about today. So the first is about the effect of alerts on driver behavior while using ADAS, and the second on driver knowledge of ADAS capabilities and limitations. So this is kind of a little bit of repetition, but I got my bachelor's in developmental cognitive neuroscience at Western, and then I worked for a couple of years and found Human Factors, and then came to U of T to do my master's. And now I'm in my third year of my PhD at U of T, and my research focuses on training and education to improve drivers' understanding of advanced driver assistance systems. And then, as mentioned, I'm part of the Human Factors and Applied Statistics Lab, or HFAST. And we do a lot of driving research, and these pictures show our simulator, which is a NADS mini-sim. We use the simulator to study automated driving, so we can set up the simulator to steer or brake for you, and so we can test how people respond when the automation fails, as I'll talk about later, which obviously we can't do in a real vehicle for ethical reasons. We don't want to be putting people in danger. We can also use a simulator to test different designs of new in-vehicle interfaces, and we can investigate how new or existing in-vehicle technologies might contribute to driver distraction, which we also can't do in a real vehicle. For safety reasons, obviously, don't want to be distracting drivers while they're driving on the roads. We also have an instrumented vehicle that we use for on-road studies, and so we use this to see how drivers allocate their attention in a real on-road environment. And so the vehicle camera that faces the road ahead, so we can see what's in the roadway. It also has a camera that faces the driver, so we can capture their facial expression and head movements. And then participants wear a head-mounted eye tracker, which is kind of like a pair of glasses, and so we can see where they're looking as they drive. And typically, how we use this is there will be an experimenter in the front who kind of gives the participant directions, and then we have a screen in the back for a second experimenter to monitor the equipment. And so on to the topic of today's webinar. Many vehicles now come with advanced driver assistance systems, and so throughout the rest of the presentation, I'll refer to these as and these help the driver with some of the driving tasks. So adaptive cruise control controls the acceleration and braking for you. So if there are no vehicles ahead, it functions like regular cruise control. So if you set your speed to 80 kilometers per hour, it will maintain that speed for you. If you're approaching a vehicle ahead that's traveling slightly slower than you, it can brake to slow your vehicle down, and it'll maintain a specified distance behind that vehicle. And then if the vehicle ahead of you speeds up, it can also accelerate your vehicle to keep that predetermined distance up until your set speed. So if the vehicle ahead of you speeds up to 90 kilometers per hour, your vehicle will speed up to that 80 kilometers that you set and then continue cruising. So lane keeping assist controls the steering, and so this system tracks the lane markings and then it steers your vehicle to keep you from drifting out of your lane. This is a taxonomy from the Society of Automotive Engineers, and so it kind of classifies the levels of driving automation, with level 5 being this like fully autonomous self-driving vehicles. And what we currently have, so these ADAS systems, are level 2. So they can control steering and braking and acceleration for you. And the important thing to note is that these are only driver support features. So they cannot drive the car for you. And so the driver is still technically driving when using these systems. It also means that drivers should be constantly monitoring the roadway, so paying attention to what's on the road, just like when you're normally driving, so that they can steer, brake, or accelerate if necessary. So in case the automation malfunctions or there's a situation that the system can't. And that's because technology is not perfect. So this image, it was from a collision in California, where a driver was using Tesla Autopilot and collided with this stopped fire truck. So if the driver wasn't using ADAS, we would expect them, if they were paying attention, to see the stopped fire truck and change lanes or brake to avoid colliding with the fire truck. One of the limitations of ACC is that it doesn't reliably detect vehicles. So in this case, the ADAS didn't stop the vehicle because it couldn't detect there was a stopped vehicle there. And the driver also wasn't paying attention and therefore didn't stop the vehicle in time either. This type of event is not uncommon. So there have been several other accidents where people have collided with stopped vehicles. And this kind of begs the question then, how can we prevent these sorts of things from happening? So one proposed solution to help drivers in these situations is a takeover request or a tour. And this is an alert that warns drivers that they need to take over full control of the vehicle. And they've been designed differently depending on the study, but generally it's an icon paired with an auditory alert that lets you know that you need to take over control of the vehicle. And so tours were the focus of the first study that I'll be discussing today. And we were interested in whether tours were equally effective for different failure types. So ADAS failures can be categorized into two types. System limit failures occur when the automation encounters a situation that we know is beyond its capabilities. So for example, we know that ACC has trouble detecting stop vehicles. We also know that lane keeping doesn't work if the lane markings are faded or missing. So this video shows an example of what could happen if lane markings are faded. So in this case, you'll see the highway splits like into a highway and an exit. And then the left marking in this lane is faded. So the car will follow this solid line almost right into the median. And so a little bit of background on this video. So there was a crash at this location where a vehicle using Tesla using autopilot crashed into this barrier. And so this video was taken by a driver who went to that location in their Tesla using autopilot to see why that collision happened. And so they knew that a failure might happen here and still were barely able to stop in time. So it shows how dangerous it can be if you don't know the limitations of the automation and you're not paying attention while you're using these systems. And so this is an example of a system limit failure because we can see why it occurred because of the known limitation being that the lane marking was faded. And so with system limit failures, there are cues in the environment that drivers can use to anticipate that this might happen. And so in this case, that would be that faded lane marking. System malfunction failures, on the other hand, are due to sensor or algorithmic errors. This could be things like the automation malfunctioning and swerving or braking when it's not supposed to. These malfunctions are unforeseen even by the designers, and so there's no indicators that a driver can use to prepare for such a failure. Recently, there are 2 recalls due to vehicles automatically braking when there's no need to. And so that would be an example of a system malfunction. There has been a previous study that compared these 2 failure types. So Dogan et al. Told participants that ACC would fail when traveling over 50 kilometers per hour. And then they had a simulator study where they asked participants to drive using this automation. And then for the system limit failure, sometimes the automation would fail at 50 kilometers per hour as expected. And in other cases, it would fail at 30 kilometers per hour. And so from the participant's point of view, there's no reason for this. And so that would be a malfunction. And so they found that drivers looked more at the speedometer speed limit, which was 50 kilometers per hour, the system limit of 50 kilometers per hour. And so that suggested that people were anticipating that the failure was going to occur because they were monitoring the speedometer as it approached that limit. They didn't find a failure type on takeover time, and takeover time is how quickly they take over full control of the vehicle. And this is probably because for both of these failures, there was a tour which let drivers know when they needed to take over. So in both cases, they were taking over when the tour kind of told them to. There is also a lot of research on tours. A meta-analysis showed that drivers take over sooner when they have a tour to alert them, which makes sense. But there's a lack of research comparing tours' effectiveness across system limit and system malfunction failures. So what we wanted to know was, are tours equally effective for these different failure types? And what we thought was tours would be more helpful for system malfunction failures because there's no other way to anticipate that these failures are going to happen. Conducted a driving simulator study. We used the head-mounted eye tracker to monitor where participants were looking while they were driving. And then as they were driving, we also gave them a secondary task on a tablet that was mounted to the right of the dashboard. And this was supposed to kind of emulate an infotainment system display that you would have in your vehicle. And we gave them a secondary task because in real vehicles, especially while using these sort of ADAS systems, people might engage in secondary tasks like changing the radio or checking their phone. And so the secondary task is provided to give them something else to do, because otherwise people who may tend to take their eyes off the road when driving, they might not do that in the simulator if there's nothing else for them to kind of direct their attention to. We had 19 participants. They all had to have a valid full driver's license for at least 2 years and be regular drivers with no reported experience with ACC or lane keeping. The secondary task that we used was adapted from previous work, and it mimicked using an infotainment system. So it was designed to be similar to searching for a song on your infotainment system, and it was self-paced, meaning that participants could choose when they wanted to engage in it. The goal was to find a matching phrase within a list of 10 phrases. And a phrase was considered a match if the first word was discover, the second word was project, or the third word was missions. And so you can see they had 2 phrases on screen at a time, and then they could use the arrows to scroll through the phrases. And when they found a match, they would tap on the screen on that match and then tap on the submit button. The automation consisted of ACC and lane keeping, and they were trained on how it worked, how to engage and disengage it, and what the limitations of both of these systems were. We also gave them a couple practice drives to become familiar with driving in the simulator. And they experienced failures in the practice drive, so that once we got to the experimental drives, the results weren't affected by shock or confusion from the first time that they experienced a failure. There were 4 experimental drives. They took place on a 2-lane rural highway with light traffic. And the task that we gave them was to follow a lead vehicle, so the vehicle ahead of them, and to drive safely. So they were told to engage the automation when they were prompted by the computer and to use it as much as possible, but to disengage it when they felt that it was necessary. And then again, they were told that they could choose when to engage in the secondary task. So our 2 independent variables were tour presence and failure type. And so tour presence was, did they get a takeover request letting them know when they should take over or not? And then failure type were the system limit or system malfunction failures. And so everything was within subjects. So all participants experienced 4 scenarios, 1 for each combination of tour presence and failure type. And so, as I mentioned, each participant completed 4 drives. So they had one of these scenarios in each drive. And then we chose to have the failures occur with the lane keeping system. And this was because a survey of Tesla Autopilot users showed that most of the unexpected or unusual events were due to failures with lane detection. So this is what the system limit failure looked like in our study. So instead of going straight through the intersection, the vehicle would follow this road edge line because of kind of the break in the lane markings here. And during training, one of the things they were told was that the automation didn't always work at intersections because of the changing lane markings. However, they were also trained on various other limitations of the system, both with lane keeping and adaptive cruise control, so they weren't just primed for this failure. And then in this picture, you can see what it looked like when they were approaching this intersection. So you can see here kind of like the lack of lane markings, and the vehicle would follow this line. And then the system malfunction failure occurred on a straight section of the road. So the vehicle veered off to the right in a similar manner to the system limit failure, but in this case, it was for seemingly no reason. In training, participants were also told that random issues might occur due to sensor errors or algorithmic failures, so that they were aware that system malfunctions were possible. And this kind of shows the view of right before the vehicle would veer off road. As I mentioned, they experienced each failure with a tour and without a tour, and this is what the tour looked like. So it would show up on screen, the bottom right hand of the front screen, 6 seconds before the failure, and was also accompanied by a loud beep, would get the participants' attention even if they weren't looking at the road. And so this graph shows how much participants were looking at the roadway versus the secondary task display in the 6 seconds leading up to the failure. So those 6 seconds because that's when the tour appeared in the tour drives. So we could compare how much attention participants were paying to the roadway when they had a tour versus when they didn't have a tour. So this left box shows the system limit failure, and the right box, the system malfunction failure. And then on the y-axis, we have the percent of time that they were looking at the roadway and the secondary task. And then the gray bars show the tour, and then the white bars are the no tour. So what we found was that the effect of the tour was only significant for system function failures when the vehicle veered off for no reason. So for these failures, participants looked more at the roadway when they had a tour and less at the secondary task. And this makes sense because with a system malfunction failure, there's no way for the participants to know when it's going to happen. And so the tour was the only way for them to know that they should start paying more attention to the roadway because they were going to have to take over control of the vehicle. For system limit failures, we don't see this the tour. In fact, participants are looking at the roadway just as much when there's no tour as when there is a tour. And this is likely because people could already anticipate that the failure was going to happen based on being able to see the intersection ahead and the knowledge that the automation didn't work well at intersections. So they were already on the roadway in anticipation of the failure and having to take over control of the vehicle, and so there's no additional benefit of the tour in that sense. And then this graph shows takeover time. So this is when participants disengaged the automation relative to the failure. So to disengage the automation, they had to either turn the steering wheel more than 5 degrees or press the lane keeping on/off button on the steering wheel. And so this dashed line indicates when the failure occurred. So values above the line mean that they took over after the failure, and then values below the line mean they took over before the failure. And then when we look at takeover time, there's a significant effect of the tour, both system limit and system malfunction failures. So without the tour, which again are the white bars, participants took over after the failure, all of them except for one. With the tour, for both failure types, on average, participants took over before the failure occurred. And so that main effect was that participants took over about 0.8 seconds sooner when they had a tour versus when they didn't. So as a summary, for the system malfunction failure, when there was a tour, participants looked more at the roadway and less at the secondary task. And again, this makes sense because participants couldn't anticipate when these malfunctions would occur. So the tour was the only way for them to know that they needed to pay more attention to the roadway immediately before the failure. For system limit failures, the TOR didn't have an effect on monitoring. So between the TOR and no TOR drives, there was no difference in how much time participants spent looking at the roadway or secondary task. And this was likely because participants were already looking at the roadway and less at the secondary task in anticipation of the failure and having to take over control of the vehicle. And so the TOR didn't provide any additional benefit, but the TOR was associated with faster takeover for both failure types. And again, this makes sense for the system malfunction failure because there's no other way for them to anticipate that it's going to happen. For the system limit, although the TOR did not affect monitoring, it did help participants take over sooner. And this could be because although maybe they could see that a failure might happen and they were anticipating that that might happen, maybe they weren't 100% sure if it would happen or when exactly it would happen. So the TOR kind of served as a confirmation that it was going to occur and prompted them to take over sooner. So some opportunities for future work include studying different types of system limit failures. So we only used one, which was the intersection, but we could also look at others, for example, poor weather or stopped vehicles. In addition, a lot of the participants didn't take over until after the failure occurred. So in our study, the failure wasn't urgent. So if they didn't take over, the vehicle would veer off into the grass, but there were no other vehicles or obstacles that they would run into. So people may have waited to take over since there was no immediate need. Nothing very dangerous would happen. Future work could increase the failure criticality to make the need to take over more urgent and see if that motivates them to take over before the failure occurs, if they can anticipate that it's going to happen. And lastly, we need to do more research on how long these effects last. So in our study, participants were trained on the limitations, and then they did the experiment right after when the limitations were still fresh in their mind. And so more work would need to be done to see whether we still see these results if there's a delay between when they learn about the ADAS limitations and then when they actually use the system. So regardless of failure type, we found that the TOR was helpful in supporting drivers to take over soon. However, it may not always be possible to provide a TOR. So for example, if the ADAS cannot detect a stopped vehicle ahead, it wouldn't be able to warn you that there is a stopped vehicle that would require you to take over. So if TORs aren't available, one thing we can do is focus on supporting drivers' understanding of ADAS, because our results showed that when drivers could anticipate the failure, they paid more attention to the roadway before that failure occurred, even without the TOR. And that kind of leads into study 2, which is the main focus of my PhD research. So we conducted an online survey, which is almost complete, to investigate drivers' understanding of ADAS in order to inform training. Studies show that in general, drivers don't have a good understanding of ACC. One study found that 70% of drivers were unaware of the ACC limitations in their vehicle. A more recent survey of Tesla autopilot users, which has ACC and LKA, found that most users rated their knowledge to be above average, but they weren't asked about any specific capabilities or limitations to confirm whether they actually did have an above average understanding of the system. And so the objective of this survey was to assess the understanding of ACC and LKA that's currently available to the public, and figure out what some of the common misperceptions of these systems are. We also asked drivers how they'd prefer to learn about ADAS so that we could inform better training in the future. 3 parts. Part 1 consisted of demographics and questions about driving habits. So how frequently do they drive? Also, if they've ever used ADAS in the past, how often they use it. And then we asked them how they have learned about ADAS and how they would prefer to learn about ADAS. And then part 2 is where we assessed their knowledge. So they completed a questionnaire where they were asked about the capabilities and limitations of current ACC and LKA systems. If they owned these systems, we asked them about the capabilities in their vehicle. If they didn't own any of these systems, we asked them, what do you think the current technology can do? And in part 2, we also asked them to rate their trust in ACC and LKA. So part 1 and 2 were the main study. Part 3 was an optional follow-up survey. And we asked them how likely they would be to engage in different secondary tasks like texting, eating, making a phone call in 4 different conditions. So while they were using no ADAS, so they're fully driving themselves, while they were using ACC only, LKA only, and both ACC and LKA. And so we use this as a measure of reliance intention. Basically the extent to which they think they would rely on the system and do these other secondary tasks while using the ADAS. We recruited participants through Mechanical Turk and online postings. They were required to have a valid driver's license and live in the United States or Canada. And for experience, we had 2 groups. So either they had to have no experience with ACC or LKA, and we called these non-owners, or they had to own a vehicle with ACC or LKA, and so these were called owners. And these are a few of the items from the ACC knowledge questionnaire, and the table shows the percentage of owners and percentage of non-owners who agreed with these different statements. So most people knew that the main function of ACC is that it keeps a set distance to vehicles driving ahead in the same lane. And most people could identify that ACC has difficulty when the sensors are blocked or dirty. But there were some common misperceptions among both owners and non-owners. So kind of around 40 to 50% of drivers thought that ACC had full braking power, which it does not. And they also thought that it would not have difficulty on curvy roads when approaching a stopped vehicle or when approaching a motorcycle, all of which are limitations of ACC, so it may not work reliably in these situations. And so these can be dangerous. So again, if a driver doesn't know or they think that the ACC doesn't have a problem when approaching a stopped vehicle, they may not take over in time and think the vehicle is going to stop when they're approaching a stopped vehicle. And it's kind of how we have these accidents happening, like I showed earlier in the presentation. For LKA, again, most people knew the main function, which is that it steers automatically, and that it might not work if sensors are blocked or dirty. 2/3 of participants knew that it would have difficulty when lane markings are faded or missing, which is a majority of the participants. But that's still 1/3 of the participants who aren't aware of this limitation, which could also be very dangerous, as we saw in the video earlier in the presentation, in which the vehicle kind of veered into that median because of faded lane markings. Some other misperceptions include over 30% of the participants thought that LKA executed evasive steering, which it doesn't. And then most people thought that it wouldn't have difficulty on city streets or when there's glare towards the driver, both of which are limitations of the system as well. So because lane keeping systems work, because they use a camera, it's sensitive to glare. So if there's glare towards the driver, there's also likely glare in the camera, which means that the system may not be able to see the lane markings. And then, as I mentioned, we also asked participants to rate their trust and reliance intention, which was their likelihood to engage in secondary tasks while using the ADAS. And what we found was that for non-owners, so these are the people who have never used any of these systems, we found that a worse understanding of ACC and LKA was associated with higher trust, and then higher trust in ACC and LKA was associated with a greater likelihood to engage in secondary tasks while using the automation. And so engaging more in these secondary tasks means more attention directed away from driving, which we don't want. And so it seems like when people aren't really aware of the limitations, they're trusting the system a little bit too much, and then kind of when we ask them if they would engage in these secondary tasks, they're more likely to do those things. On the other hand, for owners, knowledge didn't predict trust, but both knowledge and trust predicted reliance intention. So a worse understanding of the system and higher trust were associated with greater likelihood to engage in secondary tasks. And so kind of overall, what this tells us is that improving drivers' understanding of these systems, especially maybe correcting some of these misperceptions about the limitations, can have safety benefits in terms of potentially reducing their likelihood to engage in secondary tasks. And then that kind of reduces the likelihood that they're going to take their eyes off the road or be cognitively distracted when using ADAS. And so one way we can try to improve drivers' understanding of ADAS is through better training. So we also asked participants how they would like to learn about ADAS so we could focus on developing training methods that people would actually want to use. So in the survey, we presented them with the various options that you can see along the x-axis. And then we asked them to pick the top 3 methods that they would prefer to use. And so these dark gray bars show the non-owners, the lighter gray bars are the owners. And what we found was that videos were one of the most popular among both owners and non-owners. Reading the manual, also trial and error, were popular among owners specifically. And an in-vehicle tutorial was popular among non-owners. And so we looked at these results to decide what kind of training methods we would want to develop for future studies. So based on these preliminary results, we found that a large percentage of owners and non-owners had misperceptions about ACC and LKA, and that a worse understanding of these systems is associated with a higher likelihood to secondary tasks while driving. And so again, this can lead to misuse and injury if people are not paying attention to the roadway, and then they encounter a situation that the ADAS cannot handle. So if we can provide drivers with better training, hopefully they will kind of become aware of these different limitations in which they shouldn't be using the system, or the situations in which they may not, the system may not work and it will require them to. And so then hopefully they'll be using the system more appropriately. So the next steps for me are to finish the data collection on the survey and kind of finalize the analysis. And then the next experiment will be a simulator study to test the effect of different training methods on drivers. And so we want to look at, do these different training methods improve their understanding of ACC and LKA? Are some training methods better than others? Then also looking at trust. So do certain training methods provide drivers with a better understanding? Does that then also help them calibrate an appropriate level of trust in the system? And then we can look at, because it'll be a simulator study, instead of looking at whether they intend to rely on the system, get an actual measure of reliance in terms of to what extent do they still pay attention to the roadway while they're using ACC and LKA? When do they choose to use it? When do they disengage it? So if they're approaching, say, a stopped vehicle, do they know that they should disengage the automation, and do they do that ahead of time? Or do they kind of wait until the last minute and only take over once they realize that the system is not going to stop. And so based on the survey results, the current plan is to focus on owner's manual and videos. So we will have a baseline condition that receives no training, so we can kind of compare the effect of these different training methods. We are planning to use videos because they are the most popular among the participants. The owner's manual was also popular among owners, and currently this is kind of the standard way that people learn about ADAS, and it's where most of kind of the detailed information about the limitations are. So we can kind of use that to compare the current method to maybe videos, which more people want to use and more people may be more likely to use kind of on an ongoing basis. So yeah, that's kind of the plan for what I'll be doing next. Thank you very much. So that's all for me, and I'm happy to answer any questions.
Thank you so much, Chelsea, for a very current, thought-provoking presentation. I see we have some questions coming in, so I'm going to jump in, and I'm going to start with one of the earlier questions, and that is, line fading seems like a common thing. Do you know how that is being handled, or if it's being handled?
Yeah, so it is very common that roads are not continuously maintained, so there's definitely faded lane markings everywhere. So one thing that they do in current vehicle technology that's currently available is some of them have like an icon where it shows you the vehicle and it shows you the 2 lane markings on either side of your vehicle, and it will kind of light up similar to if I can kind of go back to the earlier slide, it'll show something and it'll kind of light up one side if it detects that lane marking and the other side if it detects that one. So if those lights go out, you can get the idea that the system isn't detecting the lane markings, and so that can help you. But yeah, that's what I know of that they do right now to handle faded lane markings.
Okay, thank you for that. Can you comment? You might not be able to answer all these questions, and that's okay. How are insurance companies handling accidents in terms of a fault caused by misperceptions of these ADS limitations?
Yeah, that's a really good question. I don't actually know the answer to that. I think my kind of understanding of the situation is that because these are driver support features, so the car isn't driving for you, the driver is still responsible for all of these things, and so I would assume that they would still be, from an insurance standpoint, at fault. But there are definitely factors associated with the ADAS that contribute to these collisions. So the fact that Tesla is called autopilot, people kind of get the idea that it is driving for you. And so that definitely contributes to why they're not using it properly. But technically, because it's only a driver support feature, I would think that the responsibility still lands on the driver.
Thank you, Chelsea. When you were doing your research, did you come across any statistics comparing MVA incidents among ADS and non-ADS drivers?
I did not, but that is a great question. I think the kind of the rosy outlook of ADAS is that they're going to reduce collisions, but I think that's if obviously drivers are using them properly. So it'd be very interesting to see what the statistics are, if there are any, on whether that's actually true or not.
Okay, and I have a question here about some of the methodology details of your research. How many individuals, owner versus non-owner, participated in the survey of preferred method of learning for the ADS features?
So that was the full, I think, 200, let me find the exact number. It was 220-ish for the, yeah, for the non-owners and 88 for the owners.
Great, thank you. Can you differentiate between whether the video training will take place outside the vehicle versus inside the vehicle? And does in-vehicle training refer to instructions being played on your NAV screen or some other scenario?
Yeah, so it's definitely something to consider. So we want to make sure that the different training methods are similar in the design and the way that they're provided to kind of reduce confounds between them. So the owner's manual and video training will both take place outside the vehicle so that they can be compared more easily. And then the in-vehicle training that we asked about was kind of, the idea was it would be on your infotainment system, kind of like an onboarding or a tutorial kind of pointing out features in your vehicle while you're actually in the vehicle, as opposed to like in-vehicle training, which is provided by another person kind of pointing things out to you.
Okay, thank you. Another question related to gender differences. I assume that your assessment will look at sex differences in comfort and trust in technology. Given results in risk-taking behavior with driving, I assume there may be some substantial differences. Can you comment on this?
Yeah, it's a very good point. So in general, what we're going to do, because there could be sex differences in terms of trust in the technology. The other thing we also look at is technology familiarity. So there may be differences in how familiar people are with technology or how much they kind of seek out new technology to learn. So we will look at all of these things and then also kind of include sex as a kind of moderating variable, or to see if that's kind of influencing these factors as well. So yes, definitely.
Great. In your first study, can you say why you chose 6 seconds for a TOR? Is this supported by real-life environmental cues?
Yeah, so again, very good question. 6 seconds is kind of an arbitrary time, in the sense that we picked it because this is the most commonly used TOR lead time in the literature. So there was a review that looked at kind of how what TOR lead times people generally use, and the average was 6 seconds. So that's what we used. But one thing that we're definitely considering for future studies is it even possible to provide a TOR 6 seconds ahead of time? So it might not know that early that you need to take over. And so we're kind of trying to look at the literature and talk to kind of other experts on the actual technology to see what's actually feasible. And so we can kind of design maybe a more informed TOR timing in future studies.
Thanks, Chelsea. Now going back to training. So we know that car manuals outline features. Are you aware of any training per se, instructions in a manual, or any short video training that currently exists?
Yeah, so for the survey, because the owners all had different systems, and because we asked them about the kind of capabilities and limitations of the specific system that they owned, I actually had to read all the different manuals that these owners for the vehicles that these owners had. So I've read many owner's manuals, the sections on ACC and LKA. And so you're right in that generally the way that the owner's manual is written is this is how it works. This is how you turn it on and off. This is how you change the speed setting and things like that. And then there is a section that says, you know, ACC should not be used in all scenarios. If you're in these specific situations, you should not use the ACC, and it will list things like if there is a stopped vehicle or if there are pedestrians around, if you're not on the highway. So it does list those things, but I think one of the problems is it's probably uncommon that drivers are reading the entire manual. They kind of want to go in and know, how do I turn this on? How do I turn this off? Just so they can get to the point where they can go and use it. And so those things are not necessarily highlighted, or people can easily miss those. And so videos were one way. It's kind of like a quick, short, doesn't require any reading. The video can just explain to you how the system works. And there are videos that kind of car companies have put together to explain the system. But again, the videos pretty much highlight like what the system does and how you turn it on and off, not really the limitations. So they're there and they help drivers kind of get started with using the system, but not with what all these specific limitations are. So they don't really come out of watching these videos with an understanding of the limitations. And so that's kind of when I talk about videos that I want to use for training, it'll be videos with that sort of specific information in them to kind of convey that to drivers.
Wonderful. I think your research is going to be very impactful for these automotive companies.
Thank you.
Given what you have learned from your research, would you use the driver automated features?
Yeah.
Why not?
Yeah, good question. So I would, but I also think that I am kind of hyper aware, much more aware than a normal person of all the specific conditions that I need to be looking out for when using these systems. So I think I be able to use it safely. And because I know all of these limitations, I've seen like all of these crashes that have happened while I've been kind of researching this stuff. I know that when I use it, more of a comfort system, so it is kind of just like a backup. And so I'm still looking at the road. So I have used these systems in the past, and when I do engage them, I'm still looking at the road. And then it's kind of interesting because when you lane keeping, especially, you kind of have to still be controlling the vehicle, because if you don't for a certain amount of time, it just turns off on you, which can be very dangerous if you're not steering, and then the way it reacts is that it stops steering for you. But basically the answer is yes, I do use them, but I kind of know how to use them. And I kind of only use them for fun, like to see how they work. I don't like use them regularly.
Thank you. You know, this has been an incredibly informative, stimulating presentation. And the other thing that occurs to me in terms of future research, because I have 3 adult children who are just starting to drive, is the age differentiation, if at all, in terms of results and the type of training we need to focus on.
Yeah, so that was another reason why with the survey, we asked how people would prefer to use, or sort of prefer to learn about these systems, because we were like kind of looking to figure out, are there demographic differences in how people want to learn? So maybe the younger generation wants these sort of technology centered training methods, whereas an older generation may still want to like read an owner's manual. And so we did kind of take that into account. In general, there didn't seem to be too much of a difference, but that could have been due to our sample. So this was an online survey. So even the older people who kind of completed the survey were still quite tech savvy if they were kind of on the internet doing online surveys. So we may kind of see different results if we would have done it not online. That wasn't possible because of COVID, but that's definitely something to consider. One thing we did find was that technology familiarity significantly predicted trust in the system as well. So people who kind of rated themselves as being early adopters of technology or more comfortable with technology trusted the system more, which may not necessarily be a good thing because they may be over trusting the system. But that kind of technology familiarity may also vary by age. And so it's definitely something that we're going to look at more with the data once we collect some more.
Thank you for that. And this will be our final question. Can you comment on what you have learned about human factors of L2 feature can translate and inform L3 features? That is increased automation.
Yeah, so what I would say is what I've learned is that I don't think L3 is a good idea or that it will necessarily happen. So the way that level 3 automation works is that I'll just pull this up. L3 works in that when the automation is engaged, it is technically driving. And then you only have to drive when it tells you, like when there's a takeover request. So it's basically telling you that when it's engaged, you don't have road, which I think is very dangerous, because when you give a takeover request, if it's not possible to give one, like 10, 20 seconds in advance, it's very for people to kind of reorient themselves towards the roadway. And also based on what I've learned about how the technology works, it's probably unlikely to expect that can warn you 100% of the time when there's going to be a failure. Like if it can't detect a stopped vehicle, then it can't detect that there's something there that it needs you to take over for, if that makes sense. And so, and then if it can't detect this vehicle to warn you, then it should be able to also just self. And so I think kind of the concept of level 3 maybe isn't fully going to happen the way that it's conceptualized now. That's not the answer you wanted or were looking for, but yeah, that's my thoughts on level 3.
Thank you. I want to thank everyone for joining today and encourage you to visit the CRE-MSD events page for a listing of our free webinars, including the ACE virtual summit that is taking place on October the 21st. Please don't forget to fill out your evaluation, as this is a new series for us and we are very interested in your thoughts regarding future webinars. Thank you so much and have a great day.